All right, good afternoon, evening, or morning, ladies and gentlemen. Welcome back to another episode of CS341 Algorithms, where today we're going to be talking about polynomial transformations. So what are polynomial transformations? We've seen transformations a few times throughout the course, and the difference between a transformation we've seen before and a polynomial transformation is really these are going to end up just being a subclass of the polytime reductions we've seen so far. So these are sort of like a simplified form of polytime reductions. These are going to be a format that are particularly helpful for doing things like proving NP completeness, which is something we'll see in the next video, and some impossibility results, which, for example, we'll see in the video after that. Okay, so what's a polynomial transformation? Well, it is indeed a transformation of the type that we've been seeing before, but whereas the transformations that we saw before, the reductions that we saw before in this course, we didn't really place any restrictions on, for example, how many calls to the oracle you could make. And a polynomial transformation you could think of as just being a special case of a polytime reduction where we transform the input once and we call the oracle once and we return the value that the oracle returned, true or false, as our solution. So this is about reducing one decision problem to another and calling making a single call to the oracle for the sort of sub problem that we're reducing to. Okay, so let's go through this. So for decision problem pi, let I of pi, the script I of pi, denote the set of all instances of pi. What's an instance? It's just an input. So this is the set of all possible inputs for this problem. And we're going to divide this, we're going to partition this set I of pi into I yes of pi and I no of pi. Okay, I yes is going to contain the set of all yes instances. These are inputs for which the correct answer is yes, true. Right, so we should return true for all such inputs. And then I know is the set of inputs for which we should return false or no. Okay, so this is sort of just taking the inputs and dividing them up into yes instances and no instances, and of course any correct solution to this problem pi should return true for all yes instances and no for all no instances, or false for all no instances. Okay, now suppose that pi 1 and pi 2 are decision problems. We say that there is a polynomial transformation from pi 1 to pi 2. We denote that pi 1 less than or equal to sub p pi 2 if there exists a function f that takes inputs to problem 1 and maps them onto inputs to problem 2. So we transform an input from problem 1 into an input for problem 2. And the transformation function f has to satisfy the following properties. The transformation function f and these two problems, pi 1 and pi 2, have to satisfy the following properties. Okay, so first of all, that actual transformation should take time that's polynomial in the size of the input I to the first problem, pi 1. So the problem that we're transforming from, we take an input and we transform it. We should be able to transform that input into an input for problem 2 in time that's polynomial in the size of that input I. Okay, and then additionally, if I is a yes instance to problem 1, then the transformed input should be a yes instance of problem 2. And if I is a no instance of problem 1, then the transformed input should be a no instance of problem 2. Okay, so what this is saying is that pi 1's solution, given input I, is equivalent to pi 2's solution, given input f of I. So it's saying, if you think about it, this is justifying just transforming pi 1's input into an input to pi 2, running the solution, some solution for problem pi 2, and then just immediately returning the result, because the result of running f of I in pi 2 is exactly what you should return if you're trying to solve I on pi 1. Okay? So here are the mechanics for giving a polynomial transformation. You have to specify f of I. You have to show, so in other words, f of I, we describe it as a function, but really you implement it with some code, right? You're gonna implement f of I, which is going to take I as an input. It's actually going to produce f of I. It's going to write it down somewhere, and then you'll be able to feed that as input to a solution to pi 2. Okay, so you're going to specify, you're going to write code for that transformation f of I. And then you're going to show that code runs in time polynomial in the size of the input I to the first problem. And then you're going to show that I is a yes instance of pi1 if and only if f of I is a yes instance of pi2. Okay, that's sort of wrapping up these two expressions together. We can see if I is a yes instance of pi1, then f of I is a yes instance of pi2. If I is a no instance of pi1, then f of I is a no instance of pi2. This is equivalent to just saying that I is a yes instance of pi1 if and only if f of I is a yes instance of pi2. And I'll on the next slide, I'll get into more detail about how precisely we're going to argue this. We're going to prove this on this slide and the slide after. Okay, so as I mentioned, you can think of this as a simple special case of polytime Turing reductions. So indeed, if we have a polynomial transformation from pi1 to pi2, then trivially we have a polytime Turing reduction from pi1 to pi2. This is a special case where we can only call the oracle once. So this is what one of these polynomial transformations look like. Okay, sorry, I've misspoken there. So if you want to actually produce this polytime Turing reduction given a polynomial transformation, the polynomial transformation says that there exists this f, this transformation function f, that'll map inputs of problem 1 to inputs of problem 2, satisfying those desirable properties. But of course, a polytime reduction, a polynomial time reduction from pi1 to pi2 has to solve pi1 using a solution to pi2. So how would you obtain such a reduction given this transformation function f? Well, this is what we would do. We would take the input to problem 1, and we would construct an input to problem 2 using the transformation f, and then, given the oracle for pi2, we'll call that a, just run a on the transformed input, and then return whatever the result is. And we know that whatever the result is for running a of f of I, that's going to be the correct answer to the problem, solve problem pi1 on input I. So we just run a of f of I and return the result. Okay? Now, we don't know whether I is a yes instance or a no instance of pi1 when we transform it to an instance fi of pi2, right? We can't, if we're trying to describe our transformation f, we can't design the transformation, along the lines, check if I is a yes instance. If so, transform it this way. Else, if it's a no instance, transform it that way. We can't do that, because figuring out whether I is a yes instance of pi1 is just as hard as solving pi1. In fact, that's exactly what we're doing. To solve pi1, we're trying to figure out, is I a yes instance or a no instance? So if you have the power to figure out whether I is a yes instance or a no instance of pi1, you've already solved the problem. So we don't know. We don't know whether I is a yes instance or a no instance when we transform that into an instance of problem 2. Okay, and I gave those three things that we want to prove about f of I and about I on the previous slide. So if I scroll back for 1 second to show you that, here, we had f of I is computable in polytime, then we have these two statements about the relationship between the return values of I is an input to problem I, and f of I is an input to problem 1, and f of I is an input to problem 2. That last statement up here, if I is a no instance of pi1, then f of I is a no instance of pi2, it turns out that can actually be pretty hard to prove. And we sort of saw that hinted at very briefly when I talked about the checking that the Hamiltonian cycle problem is in NP. In that case, what we did is instead of proving that statement, we proved the contrapositive of that statement. And we're actually going to do that sort of for the remainder of the course. Whenever we're working on these polynomial transformations, we're going to end up proving the contrapositive of that final statement instead. So here's the statement. If I is a no instance of pi1, then f of I is a no instance of pi2. Okay, so that's the basic statement. We're going to prove the contrapositive of that statement instead. And if you remember your logic, the contrapositive of some statement is logically equivalent to that statement. It just looks a little different. So the contrapositive of this statement, you can think of this as if p then q. Okay, so the contrapositive of if p then q is if not q then not p. Okay, so if not q, well here's q, f of I is in is a no instance of pi 2. What's not that? F of I is a yes instance of pi 2. Okay, and then, so it's if f of I is a yes instance of pi 2, then not this. Not I is a no instance of pi 1, is I is a yes instance of pi 1. So if f, the transformed input, is a yes instance of pi 2, then the original input should be a yes instance of pi 1. So we can prove this equivalent statement instead, and this statement is usually easier to reason about than this statement that's in terms of no instances, because we don't have a lot to latch onto with no instances. It's a little bit harder to prove things about them because it's not as easy to characterize a no instance as it is to characterize a yes instance. If I know something is a yes instance, I know something very strong. For example, if we were working on a Hamiltonian cycle problem, if I have a yes instance, I know there is a Hamiltonian cycle. So I can prove, I can latch onto that and use that, the existence of something with a very particular structure, to prove something about the untransformed instance. Okay. So let's see. Let me see if I got some notes here that I need to talk about. Nope. So this is all fine. Okay. So in particular, when we're sort of talking about these problems in NP, and we're talking about yes certificates and no certificates, if you remember, with yes certificates, you have something very concrete to latch onto, but the no certificates that are returned by an oracle can just sort of be any old arbitrary garbage, or they could look almost exactly like a yes instance. So you don't really learn a lot necessarily from a no instance, but you do often learn quite a bit from a yes instance. So learning that f of I is a, if you're trying to prove if f of I is a yes instance, then blah. Well, in the if part, under your assumptions that you're making as part of this proof, you know f of I is a yes instance, which means, the oracle would return a yes certificate, and you know a lot about that yes certificate. So you can prove then that there would be a yes certificate in the untransformed input to find, for example. Okay. Okay, so hopefully that's, I think if any of this is still confusing, don't worry too much. I think it'll become clear when we talk about some examples. So let me try to summarize that more convenient form of this definition that includes the contrapositive. So let pi 1 and pi 2 be decision problems. There is a polynomial transformation from pi 1 to pi 2 if and only if there exists a transformation function f that takes inputs from problem 1 and turns them into inputs to problem 2, such that f of I is computable in polynomial time on all inputs to the original problem pi 1, and that should be polynomial in the input size of I, an input to problem 1. If, such that f of I is computable in this way, and if I is the yes instance of problem 1, then the transformed input is the yes instance of problem 2, and if the transformed input is the yes instance of problem 2, then the untransformed original input should be a yes instance of problem 1. Okay, and these two statements together are if you put them together, you actually get this equivalent statement. So these two together are the same as saying I is a yes instance of problem 1, if and only if the transformed input f of I is a yes instance of problem 2. And this property is what justifies the correctness for the following sort of generic polytime reduction code. I said transformation code, but really this is the fact that this is an implementation and not just a transformation function means this is a reduction. So here's given a transformation function f, here is how you construct generically a reduction from problem 1 to problem 2. You just take the input to problem 1, feed it into f, get back fi, the transformed input that's an instance of problem 2, run the oracle for problem 2 on that transformed input, and return the result. So here's your generic polytime reduction code given a polytime transformation. Okay, so let's do an example polynomial time transformation to try to understand, what's entailed in doing that, what that entails. Okay, so let's try reducing two problems that don't seem very similar at first, but it turns out they are very similar. We're going to reduce the Clique problem to the vertex cover problem. So what's the Clique problem? Well, we have an undirected graph, G, that consists of a vertex set and an edge set, and an integer k, where k is between 1 and the number of vertices. And the question we're trying to answer is, does this graph contain a clique of size at least k or larger? And So what's a clique? Well, a clique is a subset of the vertices such that for all of the vertices in the clique, there are all possible edges between these vertices. So consider a clique W. For every pair of vertices in W, there's an edge between that pair of vertices. So for example, here's a graph with a 4 clique in it. So these nodes 2, 3, 4, 6, these form a 4 clique because there are all pairs of edges between these nodes. And note, if there's a 4 clique, then there's also a 3 clique, right? And a 2 clique, and a 1 clique. But the opposite is not necessarily true. If there's a 4 clique, that doesn't necessarily mean there's a 5 clique. Indeed, in this graph, there isn't a 5 clique. Okay, so what about vertex cover? Well, again, we take an undirected graph and an integer k, and k is up to the number of nodes. And we ask, does G contain a vertex cover of size at most k or smaller? In other words, can we use k or fewer vertices to cover the whole graph? And what does cover mean? Well, a vertex cover is a subset of the vertices that touch all of the edges in the graph. So there are two ways to look at this expression here that says the edge UV, the set of vertices UV on the endpoints of some edge are intersected with W. The vertex cover has a non-empty intersection. In other words, for every edge, take the two endpoints U and V. One of those two endpoints, or maybe both, have to be in a vertex cover. So every edge must touch a node in the vertex cover. The other way to view that expression is the k or fewer nodes in the vertex cover together have to touch every edge in G. So take the union of all the edges touched by the vertices in the vertex cover. The union of all those edges should be all of the edges in the entire graph. So for example, here's a graph with a 3 vertex cover. Okay, you can check this is a vertex cover, right? This vertex touches these two edges. This vertex touches all of those edges. So every edge in the graph is touched. In fact, only by these two vertices. So actually, there's a 2 vertex cover as well. There are multiple 2 vertex covers here. Here's one of them. So these 2 vertices will touch every edge in the graph. And notice if there's a 3 vertex cover, I mean there might be a 2 vertex cover, but you don't know. If there's a 2 vertex cover, there might be a 1 vertex cover, but you have to check. It's not the case that a large vertex cover implies the existence of a smaller vertex cover. That's not true, right? Because here you can maybe argue to yourself briefly on this graph that there is no 1 vertex cover. Now, on the flip side, if there is a 2 vertex cover, then there is a 3 vertex cover, and a 4, and a 5, and a 6, all the way up to n vertex cover, okay? So for Clique, it's harder to get bigger and bigger cliques. For vertex covers, it's harder to get smaller and smaller vertex covers. Okay, so let's do a transformation from the Clique problem to the vertex cover problem. Okay, so suppose I is an input to the Clique problem. So there's a graph and a k. And the graph's going to have some vertices, v1 to vn, and edges. And k, the size of the clique we're looking for, is going to be between 1 and n. So we're looking for a k-clique. Okay, so suppose I is an instance of the k-clique problem. Okay, so or of the clique problem with input g comma k. So we're asking the question, is there a k-clique, a clique with at least k nodes in this graph or not? Okay, so we want to solve this problem. Here's an example graph. Now, this might be sort of surprising at first, but I'm going to pull this out of this sort of, derivation of this solution, maybe out of thin air at first, and maybe it'll seem like it's sort of devoid of intuition at first, and unfortunately that's often true in these sorts of reductions because it requires a lot of time spent scratching your head and thinking about the problem and trying out all sorts of different ways of attempting to transform one problem into another until you realize there are deep connections between these problems. And so oftentimes I don't have the time or ability to describe, what these deep connections are between the problems, but I can prove to you that the connection exists once I describe the connection to you. So I'm going to do that here. What if we want to solve the Clique problem, g comma k, on this graph with this, input k? We're looking for a k-clique on this graph. How would we possibly relate this problem of finding a k-clique to the problem of finding a vertex cover? Well, my claim is there's a deep connection between the Clique problem on the graph G and the vertex cover problem on the complement graph H of G. Okay, so what's the complement graph of G? Well, it's the same nodes as G, but the edges are different. So what we do is we take every edge in G, and we make sure that that edge is not in H. And we take every pair of nodes that don't have an edge between them in G, and we add that edge to H. So we complement the set of edges in the graph. So every edge of G is a non-edge of H. Every non-edge of G is an edge of H. And if you think about how you would do this in a real implementation, suppose we used an adjacency matrix. The way you would do this is you would actually just sort of flip all the zeros and ones. So all the zeros would become ones, all the ones would become zeros in the adjacency matrix. That way, if you have an edge in the original graph, you now don't have an edge in the new graph. If you don't have an edge in the original graph, now you have that edge in the new graph. Okay? And here's my claim that'll sort of come out of nowhere at first, but I'll prove to you that it holds. So this is the result of just like a really deep analysis and understanding of a problem and trying out all sorts of different ways to try to connect these problems. So this is the part that requires a lot of creativity in doing this reduction. You have to come up with this idea that there's going to be a k-clique in G if and only if there's an n minus k vertex cover in H. Okay, so I'll prove that that's true to you. And so the idea here is going to be, if we want to solve clique G comma k, we're going to reduce that to vertex cover H, the complement graph, looking for an n minus k vertex cover. So we're going to construct a transformed graph, f of I, a transformed instance. It's not just a graph. We're going to take this input I equals G comma k, we're going to transform it into H comma n minus k. Okay, and H is going to be the complement graph. So this is an instance of vertex cover with a transformed graph, and we're looking for an n minus k vertex cover. And here, this last line where H equals this is just putting formally into mathematical notation, this procedure, this definition of what the complement graph is, how we get the complement graph from G by definition. Okay, so let's take that idea which I've presented to you without a lot of intuition, and let's just try to prove that that actually is a correct polynomial transformation from clique to vertex cover. And so I'm going to take our summarized definition of what it means for there to be a polynomial transformation between two problems, and let me plug in the specifics for this problem and explain exactly what we're trying to prove for this polynomial transformation. So I'm going to use, just for shortcuts, CL for clique and VC for vertex cover. So there is a polynomial transformation from clique to vertex cover if and only if there exists a transformation function f which takes an input to clique and transforms it into an input to vertex cover. Okay, that's our that for us, that'll be a procedure that takes the input graph G, flips all of the entries in the adjacency matrix, so we get the complement graph, and then produces the number n minus k, as the second component of the tuple of the input to vertex cover. So we're going to produce the complement graph and the n minus k. So we're going to transform the input graph comma k into the input complement graph n minus k for vertex cover. So that's our f. We want f to be computable in polynomial time for all inputs to clique. So I should be able to take any input to the clique problem and transform it in polytime in the size of that input into an input to vertex cover. Okay, and if the original graph is a yes instance of clique, the original graph and k is a yes instance of clique. In other words, if there is a k-clique, then the transformed graph, so h comma n minus k, the transformed input, which is the complement graph, and n minus k is a yes instance of vertex cover. So what we're saying here is, if there is a k-clique in the original graph, then there is an n minus k vertex cover in the transformed graph. And this last line is saying, if there is an n minus k vertex cover in the transformed input, then there is a k-clique in the original untransformed input. Okay, so that's what we're trying to prove. Let's try to show the polytime result first, and then we'll show the following two results about the return values, the correct return values. Okay, so how do we actually do this transformation? Well, I mentioned, sorry, I'll talk about that in a second. So let's just assume that we use an adjacency matrix representation here, and it actually doesn't matter whether you use an adjacency matrix representation for this complexity argument or you use an adjacency list representation. I'm going to leave it as a home exercise to try this same analysis that I'm doing on this slide with an adjacency list representation, and you should be able to see that it doesn't actually make a difference. We're still able to show that the complexity of the transformation, the complexity of computing our f of I, is still polynomial in the input size, whether you pick an adjacency list or an adjacency matrix. And for the purpose of this course, if you're trying to do a proof like this, where you're trying to show that a transformation runs in polytime, I'm fine with you assuming any reasonably efficient representation of the input. So don't pick some input that's exponentially larger than the optimal representation of the input, but you can pick, for example, any of the reasonable input representation sizes that I gave in that size of I cheat sheet table from a lecture or two ago. Okay, so here we're going to assume an adjacency matrix, which means what's the size of this input, g comma k? Well, we can represent the graph really by just the adjacency matrix. Assume the vertices are labeled 1 to n, then the columns and rows of the adjacency matrix actually implicitly represent what the names of the vertices are, and the adjacency matrix itself is enough to encode the entire graph, and the adjacency matrix size is going to be order n squared if there are n nodes. And then we also have to represent k, and to write down the number k, I could either make a unit cost assumption and assume that k can be stored in a constant number of bits, or I can, assume that maybe k could be a very, very large number, so that we don't want to assume it fits in a single word of memory, and we should, let it be an arbitrarily large number, in which case I need log k bits to write it down. Let's just go with that, and again, I'll leave it as an exercise to argue to yourself that whether I made that bit complexity assumption or that unit cost assumption, I'd still be able to prove that the complexity of this transformation is polynomial in the input size. Okay, so let's just go with this. The size is going to be theta n squared plus log k. Now we have a size. How does that relate to the actual time needed to compute f of I? So what is the time to compute f of I? Well, constructing h just means flipping the complement graph, just means flipping all the ones and zeros in the adjacency matrix, and we can do that in theta n squared time. And then because we've assumed that k is going to be potentially a huge number here, we've assumed the bit complexity model for k. Under the bit complexity model, not the unit cost model, we actually have to account for the time it takes to subtract k from n to produce this term of this transformed input. Okay, so if we're not doing the unit cost assumption, then this takes actually not a constant amount of time, but the amount of time needed to do this subtraction with, say, the grade school subtraction algorithm, where we just kind of subtract bit by bit and have, like a one carry term. That takes time, order, number of bits that we're actually subtracting. So it's sort of order length of the longer of these two numbers, and n will be the bigger of these two numbers, or it could be the same as k, but k is less than or equal to n. So this is going to be order log n bits to actually compute. So n and k will both be written down in big O of log n bits. K could be written down in fewer bits, and subtracting the two, we'll have to touch each bit, a constant number of times. So that'll take order log n time to do the subtraction. And again, my claim is if you did the unit cost model, you wouldn't it wouldn't end up changing anything in our final result. Just this term would be like a constant time term that you wouldn't have to worry about quite as much. The log term would disappear from this term, from the time term, and it would also disappear from the size term, so you'd end up being able to prove the same result. Okay, so computing f of I, by the way, this log n term will be absorbed into this dominating n squared term, right? So computing f of I takes order n squared time in total, and that's polynomial in size of I here, right? Because size of I is theta n squared plus log k, which is bigger than some constant times n squared, and this is some constant times n squared. So clearly this is polynomial in the size of the input. This is less than or equal to size of I to the c for some constant c, or this is less than or n squared. Any theta times n squared is less than or equal to big O of size of I to the c for some c. Okay, that's the sort of formal statement. Okay, so we've shown that this is actually a polytime transformation, but is it a correct transformation. Let's show this bolded line next. We're showing if G contains a k-clique, then H contains an n minus k vertex cover. Okay, so, well, suppose that G comma k is a yes instance. So there is actually a k-clique. Okay, so we'll let W be a set of k vertices that form a clique. So here's an example graph where I've drawn, some nodes that are in the clique W. This happens to be a 4-clique, and then there are some other nodes that are not part of that clique. Okay, and we're going to define W prime to be the other nodes in the graph besides the clique W. Okay, so W prime, the clique is of size k, so W prime is going to be of size n minus k. Now the claim is W prime is going to be a vertex cover in the complement graph H. Let's try to show that. So here's the complement graph, and here I've shaded W prime in H, and just notice here in the complement graph, because in G, W, the clique, it has all-to-all edges between all pairs of nodes in G, in the clique in G. And so if you think about those nodes that are part of the clique in H, because there are all-to-all edges between those pairs of nodes in G, there are no edges between those nodes in H. Okay, so for all the nodes in the clique, there are no edges between those nodes in H. That'll be useful in a moment. Okay, so let's try to disprove our claim here that W prime is a vertex cover. Okay, and hopefully we should obtain a contradiction. We should fail to disprove our claim. Okay, so let's consider any edge. We want to sort of argue to ourselves that this is a vertex cover. So we want to say every edge in the graph H should be covered. Every edge should be incident to some vertex in W prime. So consider some edge UV in H. Okay, if either U or V or both is in W prime, then we're done. It's covered by W prime. So let's assume, to obtain a contradiction, that the edge is not covered by W prime. Okay, then neither U nor V is in W prime. Well, that means U and V are both outside of W prime. And what's the set of nodes that's not W prime? Well, it's just W. So that means U and V are both in W. But what that means is there has to be an edge in H between a pair of nodes that are in this clique. But then, if we consider the original graph, this edge won't be in the original graph. But this is a clique, so this edge has to be in the original graph. So this edge cannot be both in G and in H. So that's a contradiction. So this implies that such an edge can't exist, which means every edge has to be incident to some vertex in W prime, which means W prime is a vertex cover of H. Okay, so that's one direction of this proof. Let's do the final direction. So we're going to show if H contains an n minus k vertex cover, then G contains a k-clique. Okay, so suppose f of I, H comma n minus k, is a yes instance of vertex cover. So there is an n minus k vertex cover in H. Okay, so we'll let that n minus k vertex cover be called W prime. That's going to be a vertex cover in H. And then we're going to define W to be the rest of the nodes, the other nodes, not in W prime. Okay, and this is W prime contained n minus k vertices. So W, the remainder of the vertices, it's going to be just k vertices. Okay, so our claim here is that W is actually going to be a clique in G, the original graph. Okay, certainly the picture shows us why that's true. You can sort of see this as the reverse of the case we proved on the previous slide. But, of course, we're not proving this just for this example graph. We're proving this for all graphs. Okay, so since W prime is a vertex cover of H, every edge in H touches a vertex in the vertex cover. Every edge in H has one or both endpoints in W prime. So there's no edge in H that has two endpoints in W, because every edge has to have some endpoint in W prime. So no edge has two endpoints in W. Okay, well that means there's no edge between any pair of nodes in W. in the complement graph H. But then, what that means is, in G, every edge between a pair of nodes in W must exist. So, W is a clique in G. Okay, so what we've shown here is there exists, in fact, this is an existence proof by demonstrating a particular polynomial transformation from clique to vertex cover. So we've demonstrated the existence of a polynomial transformation from clique to vertex cover by giving one specific polynomial transformation, proving that it takes polytime, proving that these three desirable properties are all satisfied. So what does this mean? If we pop back up to these three statements here, if we wanted to solve clique and we had a solution to vertex cover, we could take the input to clique, transform it into an input to vertex cover. We could do that in polytime. And then, if we just ran the vertex cover solution on that transformed input, if that solution to vertex cover returns yes, then we should also return yes. So we just return the same thing it does. And if we return yes, then if it was the correct thing for us to return yes on a given input to clique, then the transformed algorithm, the algorithm for vertex cover running on the transformed input will also return yes. So we'll do the correct thing by returning whatever it returns. Okay, so what this means is we can easily solve this problem clique now if we have a solution to vertex cover. So if we have, in particular, a polytime solution to vertex cover, we can solve the clique problem in polytime. So let's see that that's true. That's not just true for clique and polytime, it's true for any pair of decision problems that you reduce, one to the other in polytime. Okay, so consider two decision problems, pi 1 and pi 2. And suppose there is a polytime transformation from pi 1 to pi 2. And suppose pi 2 is solvable in polytime, so it's in P. Then we can also solve pi 1 in polytime. Pi 1 is also in P. So if we have pi 2 in P and we have a transformation, a polytime transformation from pi 1 to pi 2, we can prove that pi 1 is also in P. Okay, so let's see this. So suppose we have a polytime algorithm for solving pi 2. So pi 2 is in P. We'll call that algorithm A. And it's polytime, so it runs in time order m to the L for some constant L for an instance of size m. So if we run it on an instance of size m, it'll run in time m to the L for some constant L. That's what it means for it to be polytime. Okay, now suppose that we have a transformation f from problem 1 to problem 2. It's a polytime transformation. So it has complexity order n to the k on an input of size n, where k is some constant. So this is a polytime transformation. So it takes some input of size n, and in time polynomial in n, so order n to the k for some constant k, it transforms the input from problem 1 into an input for problem 2. Okay, so here's how we would solve problem 1 using the transformation, the polytime transformation, and our polytime solution for problem 2. We would take an input to problem 1. We would run our polytime transformation function to get an input for problem 2. And then we would take that input for problem 2, we run it using our polytime algorithm for problem 2. And we return whatever the result is. And this will return the correct answer, because we've proved what we need to prove for our transformation about yes instances and no instances. So this is going to give us the correct answer. We need to show that all of these steps together take polytime, though each of these steps individually takes polytime. But does it take polytime if we run all of these steps together? So let's show that. So we need to show in particular that this entire sort of reduction and execution of the oracle and return all takes time that's polynomial in the size of the input to this whole reduction. So what's the input to this whole reduction? Well, it's just the input I. So what's the size of that input? Well, let's call it n. So n is going to be size I, the input to the whole reduction. We want to show this whole reduction runs in time polynomial in n. So step 1, where we construct f of I, we've said that that runs, because it's a polytime transformation, that runs in time order n to the k. And it actually yields an instance f of I that has size order n to the k. Why is this true? Well, why can't we create like a gigantic, exponentially large f of I and produce that as a result of, running our polytime transformation function? Well, it actually takes time to write down the output of our polytime transformation. So, if we want to write down an output f of I that has n to the k bits, it actually takes n to the k time to write down all those bits. So if the runtime of our whole transformation function f takes order n to the k time, right? If that whole function takes order n to the k time to run, then we know that it can't output asymptotically more than order n to the k bits in that time. So that means the size of the actual instance of problem 2 that it produces has size at most order n to the k. And we'll call that m. M, the size of the instance of problem 2, the transformed instance, is going to be size m, which is order n to the k. Okay, now step 2, which is running the algorithm for problem 2 on the transformed input, that takes time order m to the, it's a polytime algorithm, so that takes time order m to the l, where m is the input size. M is the size of the transformed instance. Well, that transformed instance, f of I, has size order n to the k, we said, at most order n to the k. So step 2 is going to take order m, the size of that input, to the l. Well, m is order n to the k, so this is going to be order n to the k all to the l. Well, order n to the k all to the l is just order n to the kl. Okay, and order n to the kl, where k and l are both constants, is order n to some constant, which is polynomial in n. So step 2 is going to take time polynomial in n. Step 1 takes time polynomial in n. Step 2 takes time polynomial in n. The entire reduction takes time polynomial in n, and n is the size of the input I to the reduction, the input of to problem 1. So this is a polytime reduction constructed from our polytime transformation and a polytime solution, and we've plugged in a polytime solution to the subproblem pi 2. So we sort of have a polytime reduction, and we're plugging in not just an oracle that we assume runs in constant time, but in fact a real solution, A, that runs in polytime. And we're showing that this entire chunk of code to solve problem pi 1 using a polytime solution to problem pi 2 and a polytime reduction, all of it runs in time polynomial in the size of the input to problem 1. So this is a polytime solution to problem 1. Whew. Okay, that was a lot to say. Hopefully that made sense. I'm going to conclude with this slide. So not only can we, on the previous slide we saw, if we have a polytime transformation and a polytime solution to the target of the transformation, what we transformed to, if that can be solved in polytime, then we can solve the problem we transformed from in polytime. We're going to show also that polytime transformations are transitive. So if I have 3 decision problems, pi 1, pi 2, and pi 3, and I can reduce pi 1 to pi 2, and I can reduce pi 2 to pi 3 in polytime for both of those reductions, then there is a polytime reduction from pi 1 to pi 3. Okay? So if we have a polytime transformation f from pi 1 to pi 2, and another polytime transformation g from pi 2 to pi 3, we can define a transformation function h that's just the composition of f and g. In other words, h of I, the input for problem 1 is I. We can compute the input for problem 3 by taking the input for problem 1, feeding it to f, which turns it into an input for problem 2, and then feeding that problem 2 input into g, which turns it into an input for problem 3. So we can compose f and g to get a transformation h. Now, how much time does it take to actually run f and then run g on the output produced by f? And what will that runtime be as a function of the original input size I? I can leave that for you as a home exercise, but my claim is it should be very similar to the previous slide, and you should be able to show that h of I will run in polytime in the size of the original input I. Okay, so I'll leave that for you guys as an exercise, and with that we're done this first video, and next time I'm going to talk to you about NP completeness, and we're going to see our first NP complete problem and our first reduction from one NP complete problem to another, or transformation from one NP complete problem to another. All right, thanks guys, and I'll see you next time.